Hi everyone, welcome back. So just to say thank you to those who made some comments about my little video there about the Earth's core not stopping its revolutions, not stopping. And it's nice to see other people put out videos to explain what was happening there. I'll make a particular mention here of Sabine Hossenfelder. I don't know if you know Sabine's work. She has an excellent website. She's a good science communicator, a German accent, English sense of humor, wonderful stuff. I do recommend her site. But she goes into the whole thing in a little bit more detail, and she extracts information from the actual papers to illustrate the whole point. And she explains, like I did, this idea of the conservation of angular momentum. So while we're there, I'd just also like to say, call out to a couple of other websites that I've enjoyed looking at over the last few months, particularly Rebecca here, Dr. Becky, who's an astrophysicist from Oxford University. What a delight it is to watch her in action, explaining everything you could possibly imagine about astronomy and the way the universe works. So I recommend her site. Go across there and watch a few of those. I've also picked up some wonderful stuff, particularly from Zoe B. Like me, she's a teacher, and she's also caught in this teacher trap at universities where none of us are actually, well, not none of us, a large number of us aren't actually on fixed contracts. So we have to wait to the end of each term to find out whether we're going to get employed or not. It's all quite worrying on occasion. So Zoe's got some wonderful little videos there, and some of her ideas tee up nicely with mine about whether we're going to do authentic assessments, what it's like being a part-time teacher, and so on. There are hundreds of others, but I'd also like to mention Chloe. She's quite an infectious character, especially when she's working with Simone Giertz. Their video of the pair of them actually making a real working nuclear fusion reactor in Simone's workshop is wonderful to behold. Go across there and show them some love. Okay, so what I'm going to do now is come back to a different subject. I'm going to talk a little bit about a mathematical problem which popped up in my feed and which gave me food for thought. So if mathematics is your thing, stick along. We're going to just take a look at a problem which goes like this. It's, if I can work out how to write properly, I haven't used my little tablet for a while, so writing clearly on it is a challenge. So the problem was presented like this, and the question is, what are the possible values of A which will make that true? So you need to go through and think about it for a second. A simple way, and a way recommended, of course, by the great George Polya in his particular book, is just try it out. See how things go. Look for ways in which you can understand the problem with what you've already got before going on to do other things. So A cubed minus A, if we start off with 1, say let's imagine that A is 1, where does that get us? Well, what we get with A equals 1 is 1 cubed, so it should be plus A there, not minus A. 1 cubed plus 1 equals 2. And you could do another one, 3 cubed plus 3 equals, well, 3 cubed is 27 plus 3 is 30, and so on. And what you'd notice if you continued there was that when you get to 7, you've solved the problem, almost. So if I go, oops, that's my little pad here. I don't have full control sometimes, I feel. So yeah, if we now take 7 cubed plus 7, and you work it out, what you get is 343 plus 7, which does equal 350. So you appear to have a solution to the problem. They ask you what are the values of A for which that is true. But if you remember anything from school algebra, it's this, that when you have a cube in your expression, there isn't just one solution to the problem. In fact, there are three. So we're going to attack that problem a little bit, give it some thought and see where we get to. So I'm just going to rewrite the problem a bit more mathematically. I'm going to take a function of a. So I'm going to input the a's to some function and I'm just going to make it this, a cubed plus a. And now I'm going to change this top one a little bit. I'm going to subtract the 350 from both sides and I'm going to have 0 there. Now this is more like a problem you may have seen. This is a chance to find the roots of the equation. And the roots of the equation was always a bit odd. The use of language was a bit strange. What's that got to do with square roots and so on? So when I say roots of the equation, what I mean is zeros as well. And what I mean by that is, what are all the values of a which when you put them into the expression will return 0 as an answer. And for a cubic equation, which is what this one is, a cubic equation, there should be 3. We found one already, it's 7, which is very nice. So we're just going to say we found one of the roots there. We'll call it a1 just to be consistent. So a1, the root 1 is equal to 7. And I saw this expression in one of the websites. I failed to remember which one now. I think it was Student Curiosity. And what we have to do now is work out how to solve this particular cubic equation. Okay, so let's just rearrange things a little bit. Let's just rewrite our equation. And we're going to take this 350 and we're going to write it like that because we know that this is a cube. So a plus a, okay, minus 343 plus 7, which is just the 350, all of that in a bracket. Tidy that up and we end up with the linchpin of this particular problem, and that is this. I've taken the 343 and written it as the 7 cubed. I've moved that to there. So I've got a cubed minus 7 cubed plus a minus 7. And we are in that position there. Now, how do we solve from there? Now, remember that that's still equal to 0. All these are going to be equal to 0. And I'm just going to move my board up. The solution to this problem resides on something like this. We can see that this expression is the difference of 2 cubes. Now, I was familiar with the difference of 2 squares, so I confess coming across this idea that there might also be an identity, which is a cubed minus b cubed. And sure enough, if you dig through all the possibilities, if you draw your little squares, you can end up with this expression that a minus b into a squared plus ab plus b squared, that is an identity. It's always true, whatever the values of a and b might be. So this is how we are going to crack our problem open. We're going to re-express our problem in these terms here. So let's get back to it. We don't know what the value of a is, but we're going to take this a cubed minus 7 cubed and put it into the expression. A, we don't know, minus a 7, which we do know, it's one of the roots, okay? And we're going to multiply that by a squared, which we still don't know, so it stays a squared. A times b is 7 times a, so plus 7a, and the b squared is 7 squared, it's 49. Now, that's the a cube part, that's this bit. we mustn't forget in our original expression we still got this to deal with. So we have to add on to that another a minus 7. Now isn't that convenient? Because now when we take this problem, we have an a minus 7 here and an a minus 7 multiplied here. We can then factorize the expression. So moving up briefly here, a minus 7 into all of this is going to give us a minus 7 into a squared plus 7a plus 49. But then a7 into a7 gives us 1. So that is equal to 0. And we end up with the expression that we're going to use to solve the problem. A squared plus 7a plus 50 equals 0. Now straight away that tells us one of the roots, because if that whole expression equals 0, then that or both of them have got to equal to 0 also. So a minus 7 equals 0, a must be 7. And all that does is confirm our answer at the top, that one of the roots is 7, that this particular root up here is 7. So that's confirmed by this piece here. Now what we're left with is a squared plus 7a plus 50 is equal to 0. And we've got ourselves, I hope you recognize it, you may not like them at all, but he's there. This is a quadratic equation, and what we want to do now is find what are the zeros of this quadratic equation. It's got power 2 in it, so this is where the 2 remaining roots are hiding in this quadratic equation. So a squared plus 7a plus 50 equals 0. And we could spend forever working on different ways to find the solution, but we're just going to use the standard quadratic equation. So with that, remember, it's the x value, the whatever the roots are, the zeros are, is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. And in this expression, we know that a, which is the coefficient of this term here, is 1. B, the coefficient of the linear term, this bit here, is equal to 7. And C is the constant that gets left over. Our first task then is to check whether or not b squared minus 4ac is a positive number, because we don't like to take the square root of negative numbers, at least not until my next video. Okay, so b squared minus 4ac, that's going to give us a negative number, because b squared is 49 and 4 times a times c gives us 200. So we could stop there and say that there are no more roots that we can find, because that square root is a square root of a negative number. But we're not going to stop there, because there is a way to break into this pattern here. We're going to introduce the idea of the square root of minus 1. Okay, so let's just imagine that such a number exists. So let's go x is equal to minus 7, okay, minus b, minus 7, plus, or minus there, plus or minus the square root of minus 151. That's what you get when you work this piece out, all divided by 2. Okay, and that then, in that form, is the answer. There are 2 roots, minus 7 plus the square root of 151 over 2, and minus 7 minus the square root of minus 151 over 2. So there are the 2 roots, but we don't know how to actually represent them or how to get them. And I'll take a look at that in the next video. Take care, see you then.